Hello and welcome to the II Affairs podcast.
Hi, everyone. Really glad to be here to dig into this one.
Yeah, and we have a really fascinating deep dive for you today. So imagine asking a baker to reach into a fully baked cake, right?
Okay.
And somehow you ask them to extract the exact 2 cups of sugar they put in an hour ago.
Right, which is, it's physically impossible.
Exactly. Sounds totally impossible. But legally speaking, that is exactly what modern privacy laws are demanding that tech companies do with your personal data.
Yeah, it really is. It's one of the most complex engineering challenges of our time, honestly.
Because we're trying to force compliance from a system that was, fundamentally designed to absorb absolutely everything and forget nothing.
Exactly, and that's the core of the issue.
Which brings us to the mission of our deep dive today. We are exploring the wildly chaotic collision between digital privacy rights and artificial intelligence.
It's a total mess, yeah.
Right. So the law, Article 17 of the GDPR in Europe, or the CCPA in California, it says you have a fundamental right to be forgotten.
Which makes sense on paper.
Right, on paper. But how do you force a massive artificial intelligence to, unlearn something it has already absorbed?
You really can't. Not easily, anyway.
So we're going to unpack why this is just a technical nightmare. We'll break down the cutting-edge math developers are using to try and solve it. And then we'll look at a terrifying new frontier of cybersecurity.
Yeah, that part is wild. Hackers are actually weaponizing this right to be forgotten against us.
Yeah, literally using the eraser as a weapon. But to really grasp the scale of the problem, we have to contrast how we historically stored data with how AI actually processes it.
Right, because historically, if you requested deletion, a company just looked in a traditional SQL database.
Like a digital filing cabinet.
Exactly. A database is basically a highly organized filing cabinet. So the company locates the pointer to your specific row of data, they sever that pointer, and mark that space on the hard drive as writable.
And boom, the data is gone.
Yeah, it's categorical, it's just deleted.
But training a large language model, an LLM like GPT-4 or Llama, that completely breaks the filing cabinet metaphor.
Oh, totally. We are back to your cake analogy.
Right. You take billions of ingredients, internet data sets containing public information, copyrighted works, and yes, private personal data, and you mix them all together.
You mix them and you bake them.
And the data becomes hopelessly entangled across trillions of parameters.
Yeah, and let's look at the mechanics of that entanglement, because the AI isn't storing human text like a hard drive. It's not a text document.
So what is it doing?
It acts as a lossy data compression mechanism.
Lossy compression. Okay, so like when you shrink a high-resolution photo to send it over a text message, and it loses some of its crisp detail.
Yes, very similar concept, but applied to human knowledge. When an AI reads a sentence, it doesn't save the actual words.
Wait, it doesn't save the words at all?
No, not at all. It converts those words into abstract mathematical representations. It essentially plots them as coordinates in this massive multidimensional space, all based on their relationships to other concepts.
Wow. Okay.
And this creates 2 major hurdles for unlearning stochasticity and incrementality.
Okay, let's unpack those. Let's start with stochasticity.
Right. So stochasticity is just a formal word for randomness.
Randomness, okay.
Yeah. When an AI learns, it doesn't read a data set from page 1 to the end, like a human reading a book.
It skips around.
Exactly. It takes random mini batches of data, it shuffles them all up, and then it updates its internal math. And because of that randomness, we don't actually have a clear map of exactly where or how a specific piece of data influenced the final model.
Because there's no index.
Exactly. There is no index.
Okay, so that's the randomness. And what about incrementality?
Well, every single time the model adjusts its math based on a piece of data, that new state influences how it learns from the next piece of data.
Oh, I see. Everything builds on everything else.
Right. So when you ask it to forget a specific person, you are asking it to untangle a microscopic mathematical adjustment that has already, influenced billions of subsequent adjustments.
Man, that sounds impossible. Which brings up a massive risk mentioned across the research, right? Performance degradation, or what they call catastrophic unlearning.
Yeah, catastrophic unlearning is a huge issue. If you just rip out the math associated with a specific concept, you don't just lose that one fact.
You break other things.
Exactly, because the structure of modern LLMs relies heavily on multi-head self-attention mechanisms.
Okay, hold on. We should translate that for the listener.
Right.
What does a self-attention mechanism actually do in plain English?
Sure. Think of it as the AI's way of understanding context. It's constantly weighing how important every single word in a sentence is to every other word.
Right.
It's what allows the AI to know that the word bank means something totally different if the word river is nearby versus, say, the word money. Oh, that makes perfect sense. So because knowledge is distributed across this web of attention, a single concept is deeply connected to broader semantic rules.
Exactly. It's all connected.
So, like, if a company aggressively cuts out the concept of a specific copyrighted book, they might inadvertently damage the model's overall grasp of narrative structure, or even basic grammar.
Yes, exactly. The model loses fluency, it starts suffering from hallucinations, or just generating absolute nonsense.
Because you pulled a thread and unraveled the sweater.
Right, because the internal probability distribution it relies on has been structurally damaged.
Okay, so since unbaking the cake is mathematically impossible without ruining the entire cake, how are tech companies actually complying with the law?
Well, they're trying.
The research points to two main paths, right? Exact unlearning and approximate unlearning. Let's start with exact.
So exact unlearning is considered the gold standard. It really is. It is the only way to mathematically guarantee that a piece of data has been entirely forgotten.
And how does that work? The method is actually really simple. You delete the requested data from your initial training set, and then you just spend the time and money to retrain the entire model from scratch.
From absolute zero. But wait, that takes months, right? And costs tens of millions of dollars in computing power.
Oh, easily. Tens of millions.
So if a tech company had to retrain their frontier model, every single time one person out of millions invoked their privacy rights, they'd be bankrupt by Tuesday.
Yeah, it's completely unfeasible for big models.
Now, I saw an acronym in the research, CISA, S-I-S-A. The papers made it sound like a clever way to do exact unlearning without starting from absolute zero. What exactly is CISA doing?
So CISA stands for sharded, isolated, sliced, and aggregated training.
Okay, that's a mouthful.
It is, yeah. But the concept is neat. Instead of training one giant model on all the data at once, you divide the data into completely isolated buckets or shards.
Okay.
And then you train smaller submodels on each of those buckets. So if you ask for your data to be deleted, the company just finds the one specific bucket your data was in.
And they only have to retrain that one shard. That sounds like a brilliant workaround. Why isn't everyone doing that?
Well, it works well for simpler classification models, like, say, an AI designed to just recognize spam emails. But it totally falls apart for massive, large language models.
Why is that?
To understand complex, nuanced human language, an LLM really needs all the data to interact together. You can't just isolate the data into little buckets without severely degrading the AI's reasoning capabilities.
Ah, so it needs to see the whole picture to be smart. So exon learning is practically dead on arrival for the frontier models we use every day.
Pretty much.
That leaves us with approximate unlearning. If we can't retrain, we're forced to do surgery on a living model.
Yeah.
How does that mathematically work? Because the sources mention techniques like gradient subtraction and influence functions. Can we break those down?
Yeah, let's start with gradient subtraction. Think of training an AI like walking through a massive, really complex maze to find the center.
Okay, I'm with you.
The path you take is determined by the data. So gradient subtraction attempts to perfectly retrace your steps backward out of the maze.
Oh, I see.
Yeah, the engineers try to calculate the exact mathematical path a specific piece of data forced the model to take, and then they apply the exact reverse math to subtract it.
That sounds incredibly difficult. And what about influence functions?
Influence functions are, well, a bit more theoretical. Imagine a spider web.
A spider web, okay.
If you pluck one specific thread, you want to know how much the rest of the web will vibrate or shift.
Right.
So influence functions use calculus to estimate how heavily one specific training data point influenced the final parameters. It allows engineers to adjust those specific parameters without having to calculate the entire maze.
Wow. I also read about noise injection, which honestly sounds much less precise.
Oh, it is. It's very blunt.
Yeah, they basically just inject mathematical static into the specific weights where they think the memory lives.
Yeah.
Right? Just scrambling it until the AI can't recall the data clearly.
Yeah, that is a fair summary of the surgical tools currently available. And they are highly efficient because you skip the whole retraining phase,
Right.
but they are inherently imperfect.
Okay, let's pause right here and connect this to the real world because this raises a massive legal question.
Oh, definitely.
Think about your own medical records or maybe a private blog post you wrote 10 years ago. If you submit a deletion request under the GDPR and the company uses approximatory, unlearning the data hasn't actually been deleted.
Nope.
It's just been suppressed or scrambled. So are tech companies just pretending to forget?
That right there is the central tension of the entire field. There is this vast unresolved gap between privacy laws' normative goals and our current technical reality.
Because the law says delete means delete.
Exactly. The law assumes deletion is absolute, but with approximate unlearning, the model merely behaves as if it has forgotten.
It's faking it.
Essentially, yeah. The research overwhelmingly shows that residual traces of the unlearned data remain embedded deep in the model's weights.
And if it's in the weights, a clever hacker can find it.
Absolutely. Sophisticated adversaries can use techniques like model inversion.
Model inversion.
Yeah, because the model still retains the statistical shadow of your data, an attacker can feed the model-specific outputs, analyze the probability scores, and literally reverse engineer the original input.
Working backward from the answer to figure out the question.
Exactly. Or they use prompt-based exploitation.
Like jailbreaking the AI.
Yeah, basically. They construct highly specific, convoluted scenarios designed to bypass the AI's safety filters, tricking the model into relying on those suppressed residual weights.
And then it just blurts out the private information it supposedly forgot.
Yep. So, legally speaking, if a shadow of the data can still be extracted, the right to erasure hasn't truly been fulfilled.
Wait, so if approximate unlearning just covers up the data, how does a regulator actually know the data is gone? I mean, we can't just take a tech giant's word for it.
You'd hope not.
Right, they need an audit trail. But how do you mathematically prove a machine doesn't know something?
Unlearning verification is a deeply counterintuitive space. It really is. To prove an AI has forgotten something, researchers have to rely on privacy attacks.
Okay, explain that.
They take malicious attack frameworks, like tools explicitly designed by hackers to steal private data, and they reposition them as our primary defensive evaluation metrics.
This part of the research completely blew my mind. To prove the model is safe, developers literally attack their own models.
Yeah, they do. They use something called membership inference attacks, or MIA.
Let's walk through how an MIA works.
Okay. Say you ask an AI company to forget your personal blog posts. The engineers run their approximate unlearning algorithm. To verify it worked, they run an MIA against the updated model.
So they attack it.
Exactly. They bombard the AI with thousands of queries related to your blog, and they meticulously analyze the confidence scores of the model's outputs.
Now, the sources mention that they are looking for a specific success rate from this attack.
Yes, they are.
And if the attack only succeeds about 50% of the time, they declare the unlearning a success. Which, to me, why 50%? That sounds like a failure if half the time the attack worked.
I know, it sounds really bad. But statistically, a 50% success rate is a coin toss.
Oh, a coin toss.
Right. If the AI has truly forgotten the data, it has no memory to rely on, so it is forced to completely guess whether a data point was in its training set or not.
Okay, that makes sense.
So if the attack succeeds exactly 50% of the time, it mathematically proves the model is guessing. It proves the model isn't relying on a hidden memory.
Wow, okay. What about feature injection and backdoors? The papers describe this almost like a tracer die used in plumbing to find a leak.
Yeah, that's a great analogy. It is a brilliant diagnostic tool. Before they even train the model, developers deliberately inject a highly specific artificial trigger into the data they plan to delete later.
Like a secret code.
Basically, a
Right.
nonsense word, or a specific string of random numbers. After the unlearning process is run, they input that trigger. If the model reacts to it in the specific way it was trained to, they know the unlearning failed.
The die is still in the water.
Exactly. If it ignores the trigger, the unlearning worked.
I also saw mentions of snarks, spelled SNARKS, which the research calls cryptographic proofs. What are those?
Ah, snarks. They rely on zero-knowledge proofs.
Zero-knowledge proofs.
Yeah, it's a way for me to mathematically prove to you that I know a secret without ever revealing the actual secret itself.
Okay, magic. Got
It feels like magic, yeah. In unlearning, it would act as a mathematical receipt. The algorithm would generate an undeniable certificate proving that your specific data point was removed.
Without needing to run these adversarial attacks at all.
Exactly.
That sounds like the holy grail for regulators.
Oh, it absolutely is. But currently, scaling zero-knowledge proofs to models with hundreds of billions of parameters requires an unimaginable amount of computing power.
So it's just not practical yet.
No, not yet. For the foreseeable future, the industry is stuck relying on these adversarial games to audit their systems.
Which naturally leads us to the most terrifying part of this deep dive.
Yeah.
Because companies are forced to rely on these dynamic unlearning algorithms, they have inadvertently created a publicly accessible interface that alters the core model.
Yeah.
Anyone can submit a deletion request. And hackers have realized this, and they are now weaponizing the unlearning process to attack the AI itself.
It is a malicious evolution of cyber warfare, truly. Adversaries understand that if they can manipulate what the model learns and then manipulate what it is legally forced to unlearn, they can cause catastrophic damage.
Let's look at the slowdown attack. I read this as essentially a denial of service attack,
Mhm.
but specifically tailored for machine learning. How does a hacker technically snarl an algorithm like that?
Well, the unlearning algorithm uses optimization to find the easiest mathematical path to forget a data point. In a slowdown attack, the adversary poisons the initial training data set with highly complex, really tricky data samples. They tie the math into knots by making the data points heavily reliant on thousands of other variables.
Then, once the model is live, the attacker legally requests the removal of those specific samples under privacy laws.
Yes. And because the tech company is legally obligated to comply, they run the unlearning algorithm. But because the data is so deeply entangled, the algorithm just gets stuck trying to process contradictory gradients.
It just chokes on it.
Exactly. The computational cost skyrockets. It turns an easy mathematical path into an impossibly steep uphill climb, draining massive amounts of computing power.
And slowing the entire commercial service to a crawl. It's using their legal compliance against them.
Yep.
But there is a scenario in the research that is even more insidious: camouflage poisoning.
Camouflaged poisoning aims to introduce a hidden vulnerability, like a sleeper agent, into the model.
A sleeper agent.
Yeah, imagine an attacker wants to trick a medical AI into misdiagnosing a specific type of lung scan. If they just inject the poison scans into the training data, the developers will catch the anomaly during routine safety testing.
Right, they'd see it right away. So the attacker injects the malicious poison data alongside perfectly crafted mitigating data.
Exactly. This mitigating data mathematically neutralizes the poison. It just cancels it out.
So during testing, the medical model looks totally normal. It passes every single safety check and gets deployed to hospitals around the world.
And then the attacker steps out of the shadows, they invoke their privacy rights, and they formally request the unlearning of the mitigating data.
Oh my God. The tech company complies, they delete the neutralizer, and suddenly the hidden backdoor is activated in the live system.
Boom. Hospitals start getting false diagnoses. It is absolutely wild.
That is terrifying.
And again, it relies entirely on the legal obligation of the tech company to honor the deletion request. The law literally forces them to pull the pin on the grenade.
There is one more major attack mentioned, right? Over unlearning.
Oh, yeah. Over unlearning.
The attacker submits an unlearning request, but they cryptographically superimpose vast amounts of additional crucial information onto the request.
Yes, and when the system attempts to unlearn the target data, it processes those superimposed instructions and is tricked into overforgetting.
It just wipes out too much.
Way too much. It wipes out massive swaths of the model's core knowledge and just degrades its performance across all categories.
I was trying to visualize how this works, and I keep coming back to a hypnotist.
Okay.
Imagine you go to a hypnotist to erase a painful childhood memory. But right before you go under, a hacker slips the hypnotist a hidden trigger.
Right.
So when the hypnotist tries to erase just that one bad memory,
Right.
the trigger activates and accidentally wipes your entire personality and vocabulary instead.
That's actually a great way to put it.
The model is effectively lobotomized just because it tried to forget one thing.
And this phenomenon highlights a really profound paradox that the AI safety community is grappling with today.
What's the paradox?
Well, machine unlearning was supposed to be the mechanism that made artificial intelligence safer, more ethical, and compliant with human rights.
Right.
But by building a mechanism that systematically alters a trained model post-deployment, we have fundamentally increased the attack surface.
We've built a backdoor for privacy, and hackers are walking right through it.
Exactly.
So what does this all mean for us, the users? Let's take a step back and look at the whole picture. We started with a very human concept, right?
Yeah.
The right to erase your digital footprint.
Yeah.
But we've seen how that legal ideal completely collides with the mathematical reality of lossy compression and entangled neural networks.
We explored the tug-of-war between exact unlearning, which guarantees privacy but is financially impossible for large models, and approximate unlearning.
Right, approximate unlearning, which uses gradient subtraction and influence functions, but leaves dangerous residual traces hidden in the weights.
Then we looked at the bizarre world of auditing, where developers have to bombard their own models with membership inference attacks, hoping for a 50% failure rate just to prove the machine is guessing.
And finally, we ventured into the wild new frontier of cybersecurity, where hackers use slowdown attacks and camouflage poisoning to literally turn the privacy eraser into a weapon.
The transition from structured databases to probabilistic AI models has completely redefined what it means to delete something.
It's totally different now.
Yeah, erasure is no longer a binary action. It is a highly complex adversarial estimation.
Which leaves us with a truly provocative thought to mull over. We've established that to perfectly forget a piece of data, to ensure it doesn't leave a statistical trace, or break the model when removed, developers essentially need a flawless, continuous map of exactly how that data influenced every single parameter.
Right, during the entire training cycle. They have to monitor and record the data's journey continuously.
So to guarantee perfect forgetting, you need perfect tracking. So here is the paradox. If an AI requires complex, continuous tracking of data influence, just to ensure it can perfectly forget that data later, does true privacy in the age of AI require more surveillance of our data, not less?
That's a huge question.
Can a digital slate ever truly be wiped clean, or are we forever entangled in the math?
The architecture required to guarantee your privacy might, by necessity, become the ultimate surveillance apparatus.
Something to keep you awake tonight the next time you blindly check "I agree" on a privacy policy. We encourage you to stay intensely curious about how your digital footprint is managed, processed, and potentially unlearned by the tools you interact with every single day. The real rules of the internet aren't written in legislation. They are being rewritten in the hidden weights of these models. Thank you for listening, and see you next time on AI Affairs.